everyone. My name is Talia Chen. I'm in ninth grade at the Buckley School. This is Curio Crate, and today we're going to learn how do vibrations create sound. Well, here's the science behind it. Every sound we hear begins with something vibrating. Vibrations are tiny, fast movements that move back and forth that travel through the air to our ears. So here's an example. When you pluck a guitar string, like shown here, you can see it wiggling back and forth. This is a vibration. When an object vibrates, it pushes and shakes the air around it, creating what we call sound waves. Sound waves are patterns of air caused by these vibrations that carry the sounds that we hear, spreading out like ripples in the water. So imagine a rock or stone by a river. Think of this rock as an object that vibrates. When you drop that rock into the water, like here, it carries the water with it into waves, like sound waves carry sound. So instead of moving through water, sound waves move through the air. The sound waves move through the air, pushing, pulling, and bumping into air molecules along the way, carrying the sound to our ears and creating patterns of high and low air pressure. So, in other words, how do our ears catch this sound? Well, these sound waves enter our ear canal and make our eardrum vibrate. These vibrations move tiny bones in our ear, which send signals to our brain. Our brain understands and interprets these signals as sound. So as we can see here, these lines that are vibrating and moving, these are sound waves, and these enter our ear canal and make our eardrum right here vibrate. So here's a fun fact. Sound can't travel in empty space like outer space because there is no air or molecules to carry these sound waves. That's why in outer space, astronauts need radios to communicate and talk with others because there isn't any air to carry sound waves. So as we can see in these images, these astronauts have headsets on, they're using devices and technology, radio communication, transmissions, etc. to communicate with the outside world. Changes to sound. Different vibrations make different sounds. So, what is the word frequency? Well, frequency is how fast something vibrates, making the sound higher or lower. So, fast vibrations, if a small guitar string vibrates quickly or a bird chirps, it will make a high pitched sound and therefore a higher frequency. So, I'm sure if any of you have gone outside and heard a bird chirping, you can hear a very high pitched noise that they make. This means that these birds are making also a higher frequency. With slower vibrations, if a big drum vibrates slowly or a lion roars, it will make a low pitch sound and therefore a lower frequency. So here is the difference, what we see as high and low frequency. So with high frequency, we can see that the sound waves with high frequency are very narrow. They're very close together and they're very tall, right? With low frequency is the exact opposite. Here we see the sound waves are very wide. They're kind of far apart. And they're completely the opposite from high frequency. Now, amplitude. So this is how strong a vibration is, making sounds louder or softer. So if you hit a drum lightly, it will make a smaller vibration, therefore making a softer sound. But if you hit that drum way harder, it will make a bigger vibration and therefore a much louder sound. And here we have echo. So I'm sure you've heard of this word before. This is a sound wave that bounces off a surface and comes back. So if you shout in a big empty room without a carpet, a tall bathroom, or a canyon, you can hear your voice over and over again. This is a sound bouncing off the walls of the room or canyon. And we can see that portrayed here in this image. Try this at home after watching this video in your bathroom or big empty room without a carpet. And lastly, we have resonance. So this is when one object vibrating makes another object vibrate too. So if you try singing the right note near a piano, the piano string may start vibrating all by itself. If you play a string instrument like a violin and play a G, for example, on the D string, you can see the open G string vibrate along with you. Let's look at this YouTube creator to show the example of resonance with a tuning fork. So here we could see that that 512 hertz tuning fork did not make the 440 hertz tuning fork vibrate when he hit it, and therefore the ping pong ball did not move. So let's see what he does with a 440 hertz tuning fork. So here we can see that when he used a 440 hertz tuning fork and hit it, it made the other 440 hertz tuning fork vibrate as well. And this ping pong ball started moving because of that movement. So that is it for this lesson. Thank you all so much for watching.